I think it's worth making a start. Thanks to everybody who's been able to join us. My name is Rick Crossman. I'm a statistician in the Department of Mathematical Sciences at Durham University. I'm also the postgraduate teaching director, which is why I get the pleasure of talking to you all today. With me is Dr. Andrew Krause. Andrew, how would you describe your mathematical specialty?
I'm an applied mathematician in nonlinear dynamics and mathematical biology.
Thanks, Andrew. So I don't teach any of the modules that you might end up taking. Andrew, however, does, and therefore he's very kindly agreed to come and give a quick talk on the sort of maths that he teaches in his module as a way of tempting you all to come join us. And Andrew will be doing that in about 10-15 minutes after I've spoken for a little while. So I'm going to take you through a presentation on Durham in general. I'm going to take you through a presentation on the Mathematical Sciences MSc, and then Andrew will give a little presentation, a little taste of the sorts of things that you might learn on the Mathematical Sciences MSc. Most of the students who join us at postgraduate level do so for the Mathematical Sciences MSc, but there may be some of you in this chat that are thinking about doing the Centre for Particle Theory MSc. If any of you are planning on doing that, I will happily talk a little bit about that towards the end of the session as well. So let's make a start, though, with me talking about Durham in general. So I'm going to share my screen, and I'm going to take you through just a quick presentation. As I say, I am the postgraduate teaching director of the department. This is a picture of the department itself, this lovely brand new building that's only a few years old. It was even newer in that photo, which is why you can still see there's little bits of construction going on here. Just to the left of this photo, which you can't see, is a nice lake where ducks and other waterfowl like to hang out with their little babies in summer, which is a really nice sight, right? So why should you come to Durham? Well, we've got ourselves a pretty good reputation. We are currently ranked 7th in the UK. That's according to the Complete University Guide for next year. That's why it says 2025. We are also ranked 89th in the entire world. Again, and that's for next year. We are currently ranked 10th UK mathematics. So you can be sure that it's not just the university that excels, but the mathematics department itself. We are also ranked 8th in the UK for our graduate prospects. Now, when I say graduate prospects, I mean how likely graduates are to get a job when they leave us. Now, this applies to both students who have come here for an undergraduate degree and students who have come here for a postgraduate degree. I can't find, or have been unable to find any specific data with regard to postgraduates in maths specifically, but I do have some information about the sort of jobs that our students have gone on to in the last few years, which will be coming up soon. And then lastly, in terms of reputation, this is something that's very close to my heart because I've been working for a while with regard to the Athena Swan program. For those of you who haven't heard of Athena Swan before, it is a national program that was originally run within science departments, but has now been expanded to all departments at the higher education level. It is a scheme whereby you apply to get either a bronze, a silver, or a gold award. We currently hold a bronze award at the university level and at the departmental level, and that bronze award shows that we are serious about ensuring gender equality within our department. Sadly, an awful lot of maths departments in this country still see too few female students compared to male students. We are working via Athena Swan to redress that. Other reasons you should come, we have great people. Our new head of department is Professor Douglas Smith. You can see him there. You've got a picture of me when I was slightly younger, but apparently not in the best of moods. We also have lovely administrators. So if you come to us, you'll be very likely to be interacting with Suzanne or Rachel, who are the office staff that handle any crises that come up. Durham prides itself on its university community. We are the only collegiate university in the Northeast. I believe we may still be the only collegiate university in the country other than Oxford and Cambridge. What is meant by that is students are not just members of Durham University as a whole. They are also members of a specific college. When I came here as an undergraduate, I was a member of Van Milter College, and we think that the college environment and the college mentality is very much one of the things that makes Durham unique. They are places where socializing and support can be centralized. It gives students who are interested in getting involved in colleges a strong identity. And it means that rather than us just being a university of tens of thousands of students, we are a university of a dozen or so colleges on a much smaller scale, which we think gives Durham a unique character. Each of the colleges has their own facilities as well, which means, and you can use facilities from other colleges under certain circumstances. And a lot of students like to spend time visiting other colleges and socializing in that sense. We also have the Durham University Mathematical Society. Durham University Mathematical Society does extremely good work creating and strengthening the mathematical community within the department and within Durham. We are also an absolutely gorgeous location. I came to Durham as an undergraduate, fell in love with it, did my postgraduate here, did my doctorate here, moved to Warwick because that was where the money for funding was. But eventually I came back here. I just couldn't stay away. It's an extremely pretty part of the world. Durham itself is an absolutely gorgeous city, very, very small compared to many cities, but we think that's to our advantage. And there's an awful lot you can do here. You can row or boat on the River Wear. There's glorious countryside to walk through. We are very close to a number of extremely important historical sites. Durham Cathedral itself is in the centre of the city. Holy Island is only an hour or two away. Rideau Abbey is only an hour or two away. We have multiple sports facilities, both inside the university and outside the university, across the city. And the one possible downside to Durham is that some people find it a little bit on the quiet side, but you are a very quick train ride to Newcastle or Edinburgh or York if you're interested in somewhere a bit busier. Now, I said I was going to come to this. There are great opportunities that come out of Durham. I have spent some time looking at the LinkedIn profiles of our students who have left the university but still maintain contact through LinkedIn. And there are any number of jobs that a postgraduate degree helps open the door with, helps with opening the door to. If you particularly fancy the idea, you could possibly become an academic like myself or Andrew. Oxford University has our students, KPMG, Ernst & Young. Some of our students have gone on to be actuaries, project managers, consultants, risk managers. Data science is an option. Some of our students have gone on to become teachers, and at least one has gone on to be a tax advisor, and I say best of luck. And then there's a ... there to note that there's a bunch of other jobs that our students have gone on to do. So there are two MSc programs within the Mathematical Sciences department, one that we run, one that we co-run. The one that we run is the MSc in Mathematics, or more fully, the MSc in Mathematical Sciences. Our incoming program director for that program is Sasha Mangarel, who you can see in the photo there. So I'm just going to take you through a little bit about what the structure of this MSc is like. If any of you are here to think about the MSc from the Centre for Particle Theory, as I say, I'm happy to talk about that towards the end of the session, but the structure of that is extremely similar to this anyway. So even if you are interested in the CPT mathematics program rather than the mathematical science program, most of what I'm about to say in terms of structure is the same. It's just the names of the modules really that will be different. Now, one of the things we've recently introduced in the Mathematical Sciences MSc is a stream system. So what you do is you apply for the MSc in Math Science overall, but when you arrive, you'll be asked which of the streams you want to join. And that stream is there to allow you to study an area of mathematics in depth. The streams that we currently have are pure mathematics, probability, applied and physical mathematics, and financial mathematics. Each of those comes with a series of modules for you to choose from. Now, the reason why we're doing streams is twofold. Firstly, we think it's a good way of getting you to focus right from the start on which area you're most interested in. Secondly, the maths department in Durham has so many modules for you to choose from that occasionally there is clashes between modules. Now, we didn't want to deal with that by reducing the number of modules on offer because we pride ourselves on just how many different modules are being run. So instead we created streams. So within each stream, you are guaranteed there will never be a clash between modules you wish to take. If, however, you wish to take a module from outside a stream, as long as there is no clash, that isn't going to be a problem. So that's the idea behind the stream. So you'll join a stream, you'll learn from expert researchers in the field, gaining insight into the very cutting edge of mathematical theory. We teach this by extraction, which is a way of saying each of our modules that you would join is a module for undergraduates and postgraduates, which we think is a nice way of helping build a community, because you'll be talking not just to other MSc students, but the undergraduates as well. These undergraduates will almost always be in their 4th year here, so they will know an awful lot about the way Durham works, an awful lot about the city, and so being able to mingle with those students is a very good way of getting the true story about what life is like in Durham that you might not necessarily get from one of your lectures. And we've talked already about the multiple career paths that are available for you after the Maths Sci MSc, but just to drive that point home a little further, you've got research scientists, teachers, statisticians, operational researchers, investment analysts, actuaries, insurance analysts, and accountants, ... There are 3 components to the program. There is the lectures in what would generally be called the fall term, especially for our friend Nabil, who wrote this document originally. We call the fall term or the autumn term, we call it Michaelmas, for reasons I do not understand, but nobody seems to want to get rid of it. And we call our spring term Epiphany. So Michaelmas is the first term you would be with us, Epiphany is the second term you would be with us, and during those terms you would be taking a certain number of modules and going to the related lectures, again alongside undergraduates. You would then do exams at the start of our 3rd term, which is known as the Easter term. Once those exams are out of the way, you would start on your dissertation. So this is the major difference between you as postgraduates and our 4th year undergraduates. 4th year undergraduates will be doing a mathematical project. You will be doing a dissertation. The primary difference between those is mathematical projects have topics that are decided ahead of time, and then students choose from those projects. For a dissertation, you get to talk to the lecturers that you particularly have bonded with and talk to them about a specific bespoke dissertation that fulfills your needs and your interests. So what kind of modules do we have? I am, as I think I've already said, a statistician, so some of this doesn't make any sense to me, but apparently if you really dig pure maths, you can dig it through the medium of algebraic topology, analysis, codes and cryptography, Galois theory, mathematical dynamics, Riemann geometry, ... There is a picture of a torus. Probability modules, you've got Bayesian statistics, mathematical finance, decision theory, operations research. There's a couple of these will overlap with what you can do in the financial mathematics stream. Application of mathematics modules, you've got advanced quantum theory, fluid mechanics, general relativity, mathematical biology. So that, if I'm right, Andrew, that's the one you teach.
Yes, and there are 2 of them, right? So if you've done some mathematical biology before, there's, say, advanced module. If you've not done it before, then there's a more introductory module. And that's true for fluid mechanics as well.
Thank you very much. Yeah, good point. And then you've got statistical mechanics and solitons. So that's those are the three of the 4 components. The 4th component I haven't put a separate slide on, but we can look at it now. The financial mathematics stream is something that we're still tweaking. So the way this works is here are the streams for pure maths and financial maths. The modules listed in the top box are what we call level 4 modules. The modules in the bottom boxes are level 3 modules. Now that means, perhaps unsurprisingly, level 4 modules is what we offer our 4th year undergraduates. Level 3 modules is what we offer our 3rd year undergraduates. You are guaranteed that there will be no clashes in with any of the modules on the left-hand side, and you're guaranteed no clashes with any modules on the right-hand side. So you can pick any combination you want from these because these are within the streams. The only thing to bear in mind is, this is a university rule rather than a mathematical sciences rule, you are not allowed to pick more than 1 module from the bottom box. So this is a university rule that postgraduate students doing an MSc can take at most one level 3 module. So we can guarantee no clashes between stochastic analysis, stochastic processes, mathematical finance, and so on, and decision theory and operations research, but you would only be allowed to take at most one of decision theory or operations research. And then here are the equivalent lists for the probability stream and the applied mathematics and mathematical physics stream. So essentially you choose your stream, you take either 6 from the top box or 5 from the top box and 1 from the bottom. And as I say, mixing and matching between streams is not impossible, nor is it discouraged. It's simply that we cannot guarantee it will be possible for any given combination because there may be a clash. Or more rarely, or alternatively, we may not be able to, there may be prerequisite issues, by which I mean that each of these modules builds on material that you will have had to have studied in your previous degree. Okay, so on to timescale. I've mentioned the terms already. First term or Michaelmas term begins in October and lasts until the middle of December. Then we have the holiday break over Christmas and the New Year. We start Epiphany in January, and that goes on until March. Now, at that point, you'll have done your 2 terms worth of lectures. Again, this is the same for MSc for the Centre for Particle Theory. At the end of your 2nd term, you will now have gone through all of your lectures, and you are now in a position to choose your supervisor. So the way this works, as I say, is rather than supervisors ahead of time saying, this is what we want you, these are the possible dissertations you can do, pick one. The onus is on yourself to talk to somebody you would like to supervise you and come up with a dissertation topic between you that really speaks to your specific interests. And as long as you can find a supervisor who is capable of doing that, which happens almost all the time, although every now and again we do get a student with a very strong idea of a mathematical topic they want to look at, that it just so happens nobody in the department knows anything about. Rare, but not unheard of. As long as we can find somebody to help you with your dissertation, we try very hard to give you the maximum possible freedom to determine what you want to do your dissertation on. Once you've chosen your supervisor, well, it can take. So the idea is you choose it in March. It might take a little bit longer, but you then have April and May to revise before the exams that happen in the tail end of May and the first half of June. Once those are over, you're just working on your dissertation, which you then hand in September. So I hope all that makes sense. So that's everything I wanted to say with regards to the Mathematical Sciences MSc. If you have any further questions, you can email myself or you can email Sasha. I've given you Sasha's email address there, or you can email Suzanne, and I've given you her email there. Broadly speaking, it doesn't matter who you email because we all talk to each other, but Sasha would be the person to talk to if you have any academic questions or about the mathematical topics themselves. Suzanne would be a good person to ask if you have any process questions, and in particular, if you have any questions about how to apply. Okay. So starting for some time at this point, in a moment, I'm going to hand over to Andrew so he can give you a taster of what you might encounter. But does anybody have any questions for me first? Feel free to shout out or put your hand up if you have anything you'd like to ask based on what I've just said, or in general. No? Okay. A perfectly acceptable response. Then I have a question for you, Andrew. Are you able to share your screen?
Yes, let me try this now. So I should say that, right, let me do a couple of things. So I should say that Durham has a very wide mix of what I would call lighthearted or sort of enjoyable, friendly, social things, and then very serious, quite academic things. So I'll give you 2 examples of this. So one example of this is a magazine which is produced largely via Durham undergraduates, postgraduates and PhD students, but then also with lots of colleagues throughout the UK, called Chalk Dust, which is a sort of enjoyable maths magazine, nicely typeset, doing sort of fun, enjoyable things like finding optimal Pac-Man. So I'm not going to spend any time on this. I just want to mention this is one of the sort of kind of cool things you could be involved in, or at the very least, you find these sort of littered throughout the department. So a few years ago, we did something, let's say, more serious, which then became the cover issue of this this version of the magazine, and this has to do with our website Visual PDE, which we use now within quite a lot of our teaching. So if you've done a sort of first year calculus course, you've done a sort of separation of variables, of partial differential equations, you hopefully vaguely remember that they are things that look maybe like this, and then you go through a bunch of nonsense with pen and paper to solve them and get some formula like this. And then often this is where the courses end, and then you move on and you do other things. So one thing that we're trying to do at Durham, and then we're trying to spread this elsewhere, but I think we are really the ones who have created this, is the idea that this formula is fine, but we really are interested in the intuition, right? We're really interested, what does this thing look like? And you can go and do numerical analysis and programming and learn all kinds of technical things in order to solve these equations and visualize these functions. But we've taken an idea that we've stolen from Desmos and made a website where you can just type in whatever equation you want and see how things behave. So the lesson just here, for example, in this formula, the solution to this PDE, is that the amount of wiggliness in the cosine determines how quickly the thing decays in time, right? So if it's more wiggly, if m is bigger, you would expect that this exponential in time is much faster or much more quick. And then if it's less wiggly, you would expect it to be slower. And the whole point of this website is exactly to be able to test that, right? So if I make this, say, 3, you see that the thing does decay, but it decays maybe more slowly. Whereas if I make it, I don't know, 22, and it decays very quickly. And this kind of using websites and using tools, really this is developed at Durham, is something that we're trying to incorporate in more and more of our teaching. So in the more physicsy modules, here's an example of the Schrodinger equation. There are things like understanding a particle in a harmonic potential, or a sort of particle in a box that's sort of bouncing between two walls. Well, a particle in the Schrodinger equation is really a probability distribution. So if you integrate it over space, you should always get 1. And the particle isn't a point, but it's a wave. And here it's sort of bouncing between two walls, right? And so we don't use this so heavily in the very theoretical physics modules because the equations are sort of too hard to solve in a web browser, but in the kind of quite a lot of the physics modules. So particularly the solitons module and a few other modules on the theoretical physics side, we will use this sort of interactivity to let you play with this and to let you modify the equations and sort of interact with the bit of maths, I would say in a much more fun way. So the sorts of research I do, or the courses I teach, have to do with mathematical biology, particularly a theory related to Alan Turing, something called a Turing pattern. So these also appear in the sort of types of maths, partial differential equations, as these reaction diffusion systems, and they're sort of pattern forming models. And so this is an example of one of these pattern forming models. This website, if you go to it, visualpde.com, you can bring it up on your phone, and your phone will actually be doing these simulations and doing these computations. And this is something that we're using particularly quite heavily in our mathematical biology and fluid dynamics modules, but also a bit in our physics modules, a bit in, in some of the other areas. And it's the whole point of this, again, is to sort of copy Desmos, to sort of play with it and allow you to change parameters and see how this changes the dynamics of the system. You now get things that are, say, more oscillatory or different. Again, Durham is a kind of fun place where we sit between let's say humor or sort of lighthearted social things and then quite serious science. So fluid dynamics is another area. I think Zoom is right. So fluid dynamics is another area. This is a very complicated system of partial differential equations modeling water. And in the fluids courses, particularly in the advanced fluids course, which is on astrophysical and geophysical fluids, you would study this model in some detail, and it's quite a lot more complicated than things you might have seen in first or second year, and it has a number of really complex features. But in terms of understanding it at a sort of deeper level, we think that this website is one way that has helped do this, because if you simulate this model, there's a bit of lag on my machine. If you simulate this model, what you get is perhaps what you might imagine intuitively. If I poke, a glass of water, I can get ripples on the surface of the water, and then these ripples will sort of interact and they will move about, and you get these kind of waves, right? So a lot of what we do in our courses is to try and understand the dispersion and the movement of waves, to understand the properties of things like fluids, and to build a sort of consistent mathematical theory of these objects. And this is something that the UK in particular has been very good at historically. But we're now at the level where we can visualize these things very easily without having to use a supercomputer. And that's quite a bit of what we've been doing recently, is working on this visualization without having to use very sophisticated things. So something about Zoom is sort of throttling my machine. I should mention, while this is sort of lagging a bit, we, in the dissertation topics, as Rick was saying, you have a decent amount of freedom. You have a decent amount of freedom in picking your topic. So several students who have taken, say, the mathematical biology course will come and chat with me, and we will play with these software, and we'll play with other various things, and we'll have a chat about what would be a fun topic. And so one student last year did a project with me in modeling human fingerprints and understanding pattern formation there. And she's now working with me on a PhD project studying these models. These are models of little amoeba-like creatures called slime molds. And these slime molds have really quite fascinating properties. They will sort of, when you starve them, they will form slug-like protrusions, and then these will move about and interact with each other through a mechanism called chemotaxis. And again, the point of this website is that this is now a sort of interactive thing, right? So typically to simulate these equations or to study them, you have to actually write quite a bit of code. And indeed, some of our modules, you will do a bit of coding and you will explore a bit of this. But if it's not something you're interested in, but you do like looking at pretty pictures, then this is something that we've been trying to encourage a lot more in our teaching, and to sort of really push this idea of interactivity. So I'd encourage you anyway to play on this website and to sort of recognize that this has been created by someone at the University of Bath, Benjamin Walker, but then two of us at the University of Durham. Let me see, is there any, yes, and then for anyone doing proper physics or really keen to do quite theoretical physics, this is an example of something called a soliton. So these are also quite interesting sorts of waves, where they're waves that can pass through each other without affecting their height or their speed. So the taller wave is faster and it can sort of pass through the other wave without affecting it. The solitons module studies this in great depth, and these particular waves have very interesting properties. As I said, we try to have something between quite serious and quite deep science and mathematics, and things that are sort of fun. So this is an example of sort of Turing pattern simulation. You're using Turing's face as an image. And this is a particularly fun website, because if I take any other image, for example, just this random picture I find on the internet, I can take this picture and I can turn it into a Turing pattern, right? So if you go and you open up this website and you click on these things and you click here at the image, you can then take a photo of someone and turn them into a sort of horrific Turing pattern. And again, this is something that I think we encourage at Durham, is play. There's an aspect of play in how we're teaching. There's an aspect of doing quite serious, quite deep mathematics, physics, and applications, but also doing a bit of having fun and enjoying ourselves and playing around, right? So here's a lesson, for example, on this mechanism of chemotaxis I mentioned, but we've typeset this as mice chasing cheese. So this isn't in all of our teaching. Different lecturers have different styles, but particularly those of us in the applied maths group, I think, sort of sit between the world of the quite serious and the world of the sort of enjoying what's going on. Right. Let's see, is there anything else I need to say? Yes, and I should say that students will come with different dissertation topics. They will have their own ideas of what they might do, but you don't have to approach the dissertation knowing precisely what you want to do. This can evolve as a conversation with the supervisor. So I had one student this year who's working on a model in mathematical oncology, so understanding cancer, which came out of both of us chatting back and forth of various possible directions. So there is quite a bit of support. You're definitely not sort of left on your own to invent something or come up with something, but you are supported to do that if you want to, if you're keen to sort of pursue that route. I think that's all I have to say, Rick.
Thanks, Andrew, and thanks for finding a way for improving my face. I don't know whether or not we can apply that in real life. That might be quite difficult. And thank you for making that point that I really should have. Yes, I focused when I was talking on the amount of freedom you have to pick your own dissertation topic, but Andrew's quite right. If that freedom sounds daunting and you want to have a conversation with your with a potential supervisor about narrowing what might be possible, then that's perfectly reasonable as well. Thank you all very much. Thanks again for Andrew for helping me out. And I hope to see you in Durham come October.